Hi everyone, my name is Marcel and I'm doing my PhD in the group of Richard Warburton at the University of Basel. I'm part of the European Union's initial training network, which is called QUDOT-TECH. QUDOT-TECH is about making quantum technologies applicable for real life applications. There are different approaches to do quantum computing. The one we are using in QUDOT-TECH is based on single particles of light, which we call photons. In order to perform quantum computing, we do not need only sources of single photons, but we need also a camera which enables us to detect these single photons. We call it a single-photon detector. The detectors we want to use are based on superconducting materials. Superconducting materials have a high electrical resistance at room temperature, but if you put them in liquid helium, then two things happen at the same time. The temperature goes down to minus 268 degrees, and at the same time the electrical resistance drops to zero. This point where the electrical resistance drops to zero is called the critical temperature of the superconductor. In order to fabricate the detectors, we fabricate a nanowire, or that's a small wire, and this wire has a thickness between 6 and 8 nanometers and a width of about 100 nanometers. Now when a photon hits the detector, it gets absorbed, and this causes a heating which enables the superconductor to overcome the critical temperature. This leads to a switching of the electrical resistance properties, and we can measure the switching of the resistance in less than 100 picoseconds after the absorption event. The probability to detect a photon is about 95%. This combination of high efficiency and a low timing uncertainty is hardly to achieve with any other kind of detector.